Welcome, this is Coach Dorf. We're going to continue our discussion about calculus. Today we're going to talk about curve sketching. So we're going to use the ideas from calculus that we've developed in order to help us draw the graph of a function. So to do this, there's going to be some main ideas that we're going to use. Let's go over those main ideas. All right, those ideas include what is the domain of the function, where does it have its x and y intercepts. The x and y intercepts are where the graph crosses the x-axis and where it crosses the y-axis. Are there vertical and horizontal asymptotes? And if there are, where are those? Where is the function increasing and decreasing? Where does it have a local max and mins? Where is the function concave up and concave down? Are there any inflection points? And if so, where are they? And is the function odd or even? And using the fact that it's odd or even will help us then draw some symmetry about the functions. Now that's the list of what we're going to do. Let's talk about each of these individually. So first, what's the domain of the function? Well, when we look at the domain of the function, we have to be concerned about three different types of cases that could happen. One is if I have a rational expression or something that looks like a fraction. In that case, if the denominator equals 0, then that becomes something that is a restriction, and we can't have that in the domain. So this cannot equal 0. In the case of this example, x minus 3 cannot equal 0. All right, that would be excluded from my domain. If I have the square root of the function, then what's inside the square root, okay, has to be greater than or equal to 0. And the last one is if I have a log function, then what's inside or what's after the log term has to be greater than 0. Can't include 0. It can't include negative numbers. All right, what's the next case that we have? X and Y intercepts. So the x-intercepts are where the graph crosses the x-axis. That's why it's called x-intercepts, x-axis. To find those, though, what we usually do then is to let y equal 0 and we solve for x. So that will give us our x-intercepts. So again, it's where it crosses the x-axis. Y-intercepts, in the same type of line here, is where the graph crosses the y-axis. And to find those, we let x equal 0 and we solve for y. All right, next, we have vertical and horizontal asymptotes. So vertical asymptotes, these occur when the denominator of a fraction equals 0. So earlier we had an example, and we saw that the denominator of a fraction was x minus 3. And so where that x minus 3 equals 0, then that's where we have a vertical asymptote. Horizontal asymptotes occur when the graph approaches a value as x gets really, really large. So it goes very far to the right on the graph, or x gets really, really small, and that's going very far to the left. All right. The next one is where the function is increasing or decreasing. So if the derivative is greater than 0, then the graph of f is increasing, and if the derivative is less than 0, it's decreasing. Now we're going through all of these, all right, really quickly. After we get done with these, we'll do a specific example to demonstrate how to find all of these in a case. All right. 5, where there's local max or mins. This occurs if the graph goes from increasing to decreasing. So right where it goes increasing, decreasing, that we have a local max there. And likewise, we have a local min if it changes from decreasing to increasing, that has then a local min occurs there. Okay. Concave up and concave down. So the graph of f is concave up if the second derivative is greater than 0. And again, I like to think of that as second derivative is positive, so we have a plus. I write 2 positives here because it's the second derivative, and that gives me a smiley face, and it's concave up. If the graph is concave down, if the second derivative is negative, and so since it's negative, we have a negative sign here. I write 2 of these because it's the second derivative, and that gives me my frowny face or my stormtrooper face, and it's concave down. Inflection points occur when the graph changes from concave up to concave down, or from concave down to concave up. And last, we have odd and even functions. F of x is even if I look at f of negative x, and if that equals the original function f of x. Okay, a graph of an even function is reflected across the y-axis. So a good example of this is f of x equals x squared. And you can remember that that's an even function. It has an even power. It has even power. The power is 2. And so I look at this f of, in this case, of -2, that means I put, excuse me, f of negative x, that means I put negative x in, I square it, and then I get positive x squared, which is the same thing as f of x. So that gives me an example of an even function. And the graph of it is the u. If I take what's the blue part and I reflect it across the y-axis here, I get the corresponding red part on the left side. For an odd function, I do the same thing. I look at f of negative x, but in this case, I don't get f of x, but I get negative f of x as it. And the graph of an odd function is rotated 180 degrees about the origin. An example of this would be f of x equals x cubed. So I have the blue part, and now if I rotate that, if I put a pin at the origin and I rotate that blue part 180 degrees, I get the red part shown here. And to see that it's an odd function, if I put in negative x, that means I have negative x cubed in this case, which is going to give me negative x squared, which is negative of the original function. So it's an odd function there. All right. So those demonstrate all the principles or all the ideas that we're going to talk about that we had at the very beginning here. That we look at the domain of the function, we look at the x and y intercepts, we look at vertical and horizontal asymptotes, where it's increasing, decreasing, local max and mins, concave up, concave down, inflection points, and odd and even functions. All right, let's look at a specific example of using those 8 ideas we talked about in order to sketch the graph of this function. So the first idea was the domain. So 1, domain of this function. So we have the function f of x equals x minus 2 over x plus 1. We have a rational expression here, looks like a fraction. We know then that x plus 1 cannot equal 0, because then we'd have 0 in the denominator. That means that x cannot equal -1. So my domain is going to be -infinity to -1, union -1 to infinity. Second, we do the intercepts, the x and y intercepts. So the x-intercept is where the graph crosses the x-axis. So if I have my graph here, where does the grid here, where does my graph cross the x-axis here? That would be the same thing as we let y equal 0 and solve for x. So in this case, that's going to be x minus 2 over x plus 1 equals 0. When I have that, that means I want to let my numerator equal 0. So this is going to give me x minus 2 equals 0, or x is going to equal 2. This then is my x-intercept. But it's often useful to write this as a point, a set of ordered pair, x and y. So I'm going to note here then that my x and y values are going to be 2, 0. The 2 coming from here and the 0 coming from where you let y equal 0. All right, my y-intercept, we're going to let x equals 0 and solve for y. So in my function, remember my function again was x minus 2 over x plus 1. So we have now f of 0 is 0 minus 2 over 0 plus 1, and I get -2 over 1 or -2. Then this -2 is my y-intercept. Make sure emphasize the -2 there. But again, like before, it's useful to have that as an xy point. So my x point is 0 and my y point is -2, where the 0 comes from the fact that we let x equal 0, and the -2 comes from my y-intercept right there. Okay, and I'm going to circle these because we're going to come back to these later. So I've got the point 0, -2, and I have the point 2, 0. And we'll just go back and in the domain, we'll circle that because we have that back there. All right, the third thing that we talked about looking at, were the asymptotes. All right, so we have vertical and horizontal asymptotes. We have a vertical asymptote. That's where the denominator can equal 0. And we saw earlier that in this case here, let me do this in green here, that x cannot equal -1. So if I look at my original function, again, I have f of x equals x minus 2 over x plus 1. The problem, we would have a vertical asymptote at x plus 1. So x plus 1 equals 0. So x equals -1. This is my vertical asymptote here. And if I were to draw a graph of my function, remember what that means is that at the point -1, I'm going to have a set of dotted lines here that the graph doesn't cross. That's a vertical asymptote. Try to draw those. Guess I think you can see that there. Okay, where do I have a horizontal asymptote? So horizontal asymptote, that's when I look at what happens when x gets really, really large, when I go very far to the right, and when x gets really far to the left. So to do that, we look at the limit as x goes to infinity of my function, f of x. So it's the limit as x goes to infinity of x minus 2 over x plus 1. Now, we've talked several different ways to do this. We can now use L'Hopital's rule, which is probably the easiest way. If I try to do like a direct substitution, that means I put in a very large number for x and a very large number in for x, for the numerator and the denominator. And when I do that, I'm going to get infinity over infinity, which is an indeterminate form. So we can now use L'Hopital's rule. So by L'Hopital's rule, which I'll put down LH here, I take the derivative of the top and I get 1, and the derivative of the bottom, I get 1. And so I get 1 there. So the limit there equals 1. So there is a horizontal asymptote at y equals 1. And so that means in my graph here, here's the value 1, that it's going to be approaching 1 when I go very far to the right. To go very far to the left, I'm going to do the limit as x goes to -infinity of f of x. All right, so I'm going to have that limit as x goes to -infinity of x minus 1 over x plus 1. And when I do that, I get a really, really small number on the top and a really, really small number on the bottom. All right, so you can think of it as infinity over infinity. I do L'Hopital's rule again here. And when I do that, I get the limit as x goes to -infinity of 1 over 1, which gives me 1. So there's a horizontal asymptote at y equals 1, and that's from the left side. So in my graph, let's see, let me just re-emphasize this. The first one we did was from the right side, and maybe I will draw that in red and get this to work. Okay, and then that's this one. And in blue, we have that also happening over here, but that one's coming from the left side there. Okay, so those are my horizontal asymptotes. That was number 3. So number 4, we're going to look at where it's increasing and decreasing. Okay, so I'm going to look at the derivative here. Again, my function was x minus 2 over x plus 1. So now we want to look at the derivative here. So that's going to be x plus 1. So the denominator times the derivative of the top, which is going to be 1, minus the top times the derivative of the denominator, which is 1 all over the denominator squared. All right, so that's going to give me x plus 1 minus x minus 2 over x plus 1 squared, which is going to give me x plus 1 minus x plus 2. Make sure you get a plus 2 there, because you have that negative, and that goes to both terms here. So that's going to make it into a plus 2 in the numerator, and then in the denominator I have x plus 1 squared. So that's going to give me 3 over x plus 1 quantity squared. So we need to find what are the critical numbers here. There are no critical numbers because the numerator can never, the derivative never equals 0 because the numerator never equals 0. But the function doesn't have, as we saw earlier in part 1, the domain is restricted because of -1. So when I make my table here, I'm going to look at these intervals from -infinity to -1 and from -1 to infinity. All right, so I look at the first derivative here because we're trying to find increasing and decreasing. I take a point inside that first interval from -infinity to -1. I substitute into the derivative. We're going to take the point -2. When I do that, and I plug that into my derivative function here, we'll see that I will get something that is greater than 0. And so it's increasing on there. And now I'll take a point inside the second interval from -1 to infinity. I'll take 0. When I plug that in into my derivative here, I see that that's greater than 0. So the function is increasing on both of those intervals there. All right, so nowhere it's decreasing, it's always increasing. 5 local max and mins. And we do this by seeing where does it change from increasing to decreasing. So in this case, there's none because it's increasing in both of my intervals there. All right, part 6, we want to do concave up and concave down. So we're looking at the concavity. So I'm going to look at the second derivative. Remember, we just did the first derivative. Well, let's see. Let me rewrite this. Let's just start from the beginning. The original function was x minus 2 over x plus 1. We found the first derivative in part 4. And in that case, we had that red part up here. We'll just put it now circled in blue. Okay, so that was 3 over x plus 1 quantity squared. I'm going to write that as 3 times x plus 1 to the -2. I could use the quotient rule to find the second derivative because we have this. I could do the quotient rule to find the derivative, but there's no x's in the numerator. So I think it's easier if we write it like this in green. And so I'm going to use that now to find the second derivative. So I'm taking the derivative of what's in the green. So by the power rule, I've got the 3 out front. By the power rule, I'm going to put the -2 out front, and then I write x plus 1, and I reduce the exponent by 1. So that's going to give me 3. And then by the chain rule, I have to take the derivative of what's inside. So ddx of x plus 1. But when I do that, that's just going to be 1. So the second derivative is going to equal -6 x plus 1 to the -3 power, or I could write that as -6, and then the denominator x plus 1 cubed. Okay, so now I'm going to make my table, and I'm going to have my intervals from -infinity to -1 again, and -1 to infinity. Okay, the second derivative never equals 0 because I have a -6 in the numerator, so I don't have any points, critical points for the second derivative there, but I do have the fact that at -1, the denominator is not defined, so I'll use that to make my intervals. And we're going to now evaluate those intervals, a point in those intervals, and plug it into the second derivative. So the second derivative, I'm going to take the point -2. When I put that into what I have here in purple for my second derivative, I'm going to see that that is going to be a negative on top, and I'm going to get a negative on the bottom, and therefore it should be greater than 0. And so that's going to be, I'll use my little thing here. it's greater than 0, so I have 2 pluses, smiley face, so it's concave up. If I take a point in the second interval, like 0, when I plug 0 into the purple expression, I get a negative on top, I get a positive on the bottom, so that's going to be negative. Then I use my little thing, get frowny face or stormtrooper, and that's concave down on that interval. Okay. Then let's see, what do we have next? Inflection points. Inflection points. Well, it does change from concave up and concave down that we saw right here. And I'll put in green. Goes from concave up to concave down. But x equals that. Where does that happen? That happens at negative x equals -1. But x equals -1 is not in my domain. So there is no inflection point because where it changes from concave up to concave down is not in my domain. So there are none inflection points, no inflection points. Yeah, that's really bad. Inflection points, there are none of those because there are no inflection points because where it changes from concave up to concave down is not in my domain. Okay, and then last thing, even and odd. Is this an even or an odd function? Well, I'm just going to look at, let me write down my original function again. So I've got the original function was x minus 2 over x plus 1. So now I'm going to look at the negative of that. So that means I put in negative x wherever there was an x. I have negative x here. And now I simplify that, I get negative x minus 2 over negative x plus 1. Let's multiply top and bottom by -1 to get it to look in a nicer form. That means on the top, I'm going to have x plus 2 over x minus 1. And how does this compare to my original function? Is it the same? Well, no. Okay, so f of negative x does not equal the original function because the signs here are different than what I get here. How about if I did, does f of negative x equal negative f of x? If I multiply by a negative in there, does it get the same thing? And the answer is no, it doesn't get that. If I multiply by, because negative f of x would be negative of x minus 2 over x plus 1, and that would equal negative x plus 2 over x plus 1. But that doesn't look at all like this. So the f of negative x does not equal negative f of x. So it's not odd. And this one, it's not even. So it's none of those. All right. And then the last thing, let's sketch the graph of this. Sketch the graph. So I'm going to draw an axis here. And I know that x equals -1. So if we go back let's go back to question number 2. So way back here we'll go all the way to the beginning. So the domain here, draw this in green, we have the domain is there. What's important now are these x and y intercepts. Remember how we figured these points, x, y was 2, 0. So the x-intercept is x equals 2, and that gave us the point 2, 0. And then the y-intercept was -2, that gave us the point 0, -2. So let's put those into our graph here. We had the points, let me write those down again. We had the points 2, 0, and we had the point 0, -2. So we're going to draw those into our graph. I'll use red there. So here's the point 2, 0. And if I draw in -2 here, we also have this point. Okay, so those are my 2 points. Here's this point, and here's that point. Okay, going back then to some of the work that we've done in part 3, we have asymptotes. We have a vertical asymptote at x equals -1, and we have a horizontal asymptote at y equals 1. All right, so let's do that here. We've got vertical asymptote at x equals -1. So that means in red here, we're going to have a dotted line like this. And we have horizontal asymptote at y equals 1. So that means as we go really far over here, my graph should approach this way and should approach that. Okay, maybe I should draw those. Well, I don't need to draw those in red. Okay, then let's see, what did we have next? We had increasing and decreasing. So we saw that it was increasing. Let me draw this in a different color. Increasing on both of these intervals from -infinity to -1 and -1 to infinity. All right, so we're increasing on -infinity to -1 and from -1 to infinity here. Okay. Let's see. With the horizontal asymptote, I'm going to draw in a dotted line here to connect these here. So we've got that, and we've got this. And here's my horizontal line. You can cross the horizontal line, but it just means as it goes further on, that's what's going to happen. I don't see how I can use quite that it's increasing yet here. I do know that there's going to be this vertical asymptote. So if it's increasing from -infinity to -1, and there's a vertical asymptote here at -1, that means it's going to have to be going up like this. And if I've got a horizontal asymptote on the far left, it's going to be going like this. So it's going to be increasing in this interval. So I'm going to say my function is going to look kind of like that. Also, it's increasing from -1 to infinity. I know that there's going to be this horizontal asymptote at x equals -1. And I have these points that it has to go through that we got from question number 2. So I'm thinking it's going to look something like this. So that gives me my guess about what my function is. Let me draw this in blue so that it sticks out maybe a little bit more. I'm thinking my function is going to look something like this. And we're just going to check the rest of the information to make sure that it corresponds correctly. Okay, so we've done where it's increasing and decreasing. Remember, for part 5, we found that there were no local max, and that fits in with the blue graph that I drew here, part 8. All right. Concavity, we found that it was concave up from -infinity to -1 and concave down from -1 to infinity. So we had concave up from -infinity to -1 and concave down from -1 to infinity. And that matches what we have right now in our graph, right? Concave up here, trying to redraw my graph, and concave down here. Okay. Then we had in part 7, no inflection points. Whoops. And that matches with what we have, no inflection points. Part 8, odd and even function. It's not an odd or an even function. So it's not, if it was an even function, I could take the reflection across the x-axis, but that doesn't happen here. And if it was an odd function, I could rotate what's to the right of the y-axis and rotate that 180 degrees, and I would get the left part. But it's not odd or even, so we get this, and we're done. That's the graph of our sketch of the graph of our function. Again, for our function, f of x equals the original one was x minus 2 over x plus 1. this is what the graph of it looks like. All right, thank you. Hope that helps.